In this skill, we again have an acid and a base reacting where one of them is weak and one of them is strong. However, this time we're going to have an excess of the weak reactant. We're going to be figuring out our excess of H plus or OH minus ions once the solution is at equilibrium and using that to figure out the pH of our solution in the end. In this particular question, we mix 0.710 moles of perchloric acid with 1.12 moles of ammonia solution at 25 degrees C. We're told the total volume of the solution is 0.971 litres. So we can see here we've got our perchloric acid and our ammonia reacting to form our product here. However, in our net ionic equation, we don't see the ClO4 minus ion because that appears in both the reactants and the products. It's a spectator ion, so it's been ignored. We just see the H plus reacting with the NH3 to form NH4 plus. So this is our weak base. And NH4 plus is the conjugate acid that's formed. First, let's figure out how many moles of our weak base and our conjugate acid will be remaining after the reaction has taken place. So we had 0.710 moles of HClO4 and 1.12 moles of NH3 reacting together. We can see from our molecular equation that is in a 1-to-1 ratio. We have 1 mole of HClO4 reacting with 1 mole of NH3. So since it's a 1-to-1 ratio, it's really easy to tell that 0.710 moles of the ammonia is going to be used up reacting with the perchloric acid. And we're going to be left with 1.12 minus 0.710, which is 0.410 moles of NH3 left at the end. So of the 1.12 moles of ammonia that we started with, 0.410 moles will be remaining as ammonia. The rest, the remaining 0.710 moles, that reacted to form ammonium ions. So those are going to be our equilibrium moles of ammonia and ammonium ions. So for ammonia, it's 0.410. For ammonium, it's 0.710. Awesome. Next, we need to find our concentrations or our molarities for each of those. Let's head to the reference sheet. Here's the molarity equation. Molarity is equal to number of moles divided by volume. Molarity is equal to number of moles divided by volume. So for NH3, the number of moles is 0.41. Divided by the volume, we're told in the question the total volume of the solution is 0.971 litres. That gets us a concentration of 0.422 molar for NH3. And for ammonia, we had 0.71 moles divided by the volume of 0.971 litres, which gets us a concentration of 0.731 molar for NH4 plus. So let's go ahead and fill those answers in right here. Awesome. Now we're going to be ending up with some ammonia and some ammonium ions. So we're going to have that weak base and conjugate acid still remaining in our solution, and they will be converting backwards and forwards between each other. Here we have the equation that shows that. Ammonia reacts with water according to the following equation. So we have the ammonia forming ammonium and hydroxide ions with this Kb value. So let's go ahead and write an expression for Kb for this reaction, the base dissociation constant. Here on the acids and bases reference sheet, we can see the base dissociation constant, Kb, is OH minus times the concentration of the conjugate acid divided by the concentration of the base. So it's going to be concentration of OH minus times the concentration of the conjugate acid divided by the concentration of the base. So let's put in our formulas for this problem. The conjugate acid is going to be NH4 plus, and the base is NH3. So our conjugate acid up here is NH4 plus, and our base is NH3. So we can go ahead and fill that in here. We've got OH minus and NH4 plus on the top and NH3 on the bottom. Awesome. Our next step is going to be using the ICE table to figure out what our equilibrium concentrations of each of these things will be. So our initial concentrations, those are what we had at the end of our reaction. At the end of our reaction, we had 0.422 moles of ammonia. We had 0.731 moles of ammonium. And we're not going to have any hydroxide ions to start with. Then these are going to come to an equilibrium. So if our ammonia gets used up, if we use up X of ammonia, we're going to produce X of ammonium and X of hydroxide ions. So our change in concentration in terms of X is going to be negative X for NH3, positive X for NH4 plus, and positive X for OH minus. To get our equilibrium concentration, we just add the initial and the change. So that's going to be 0.422 minus X for NH3. It's going to be 0.731 plus X for NH4 plus, and it's going to be 0 plus X, which is just X for OH minus. However, we are going to be using the small x approximation here. The small x approximation tells us that if we add or subtract a really small number, x, from a bigger number, it's basically not going to have any effect on the bigger number because x is so small. So for both our NH3 and our NH4 plus equilibrium concentrations, we're just going to get rid of the minus x or the plus x and say that our concentration is going to be unchanged from the initial. Because that change, x, is so small, it's not actually going to affect our number. That is going to help to make our algebra a lot simpler. We now know our Kb and we know our equilibrium concentrations apart from x, so we can substitute that all into our Kb equation to figure out what x is. So we're given Kb in the question as 1.80 times 10 to the power of negative 5. OH minus, the concentration is going to be X from our equilibrium concentration row. NH4 plus, the concentration is 0.731, divided by the concentration of NH3, which is 0.422. I'm going to multiply by 0.422 on both sides so that I cancel that on the right. And I'm going to divide by 0.731 on both sides, so that also cancels on the right. I'm left with x is equal to 0.422 multiplied by 1.80 times 10 to the power of negative 5 divided by 0.731. So if we put that into a calculator, we're going to get out an x value of 1.04 times 10 to the power of negative 5. So we can go ahead and fill in our change in concentration row now that we know what x is. For NH3, it's minus 0.14 times 10 to the power of, written as E on this platform, negative 5. And then for ammonium and hydroxide, it's going to be positive 1.04 times 10 to the power of negative 5. Then for our equilibrium concentrations, for hydroxide, it's going to be exactly the same as the change since it was added to 0. So that's also going to be 1.04 times 10 to the power of negative 5. And then for ammonia and ammonium, we use that small x approximation, but we can just check that that made sense. So for ammonia, our equilibrium concentration would be 0.422 minus 1.04 times 10 to the power of negative 5. If I put that in my calculator, I'm just going to get 0.422 when I round to 3 significant figures. Let's check for NH4 plus. We had 0.731 and we're adding 1.04 times 10 to the power of negative 5. If I put that into my calculator, again, I'm just going to get 0.731 when we round to 3 significant figures. So there's essentially no change in our numbers from the initial to the equilibrium because the x was so small. So we can go ahead and fill those numbers now. Awesome. So now we know our equilibrium concentrations, including the equilibrium concentration of OH minus. We can go ahead and find the pH by first finding the pOH. Here's our pOH equation. pOH is equal to negative log the concentration of OH minus. And we just calculated the equilibrium concentration of OH minus. It was 1.04 times 10 to the power of negative 5. So if we put that into our calculator, that's going to get us a pOH value of 4.98. Let's go ahead and fill that in. Finally, to find our pH, we can use this equation to convert between pH and pOH at 25 degrees C. pH plus pOH is equal to 14. We're trying to find pH, so we're going to subtract pOH from both sides so that will cancel out on the left, leaving us with pH is equal to 14 minus pOH. We can put our numbers in. pOH was 4.98. That leaves us with a pH of 9.02. So we can go ahead and fill that in now. Awesome. So again, there's a lot of steps in this question. In this one, we had an acid and a base reacting together, one strong and one weak. The weak one was in excess. In this question, we had a weak base in excess. As a result, our final pH was greater than 7, meaning the solution was basic because we had extra base left over at the end. Because it was a weak base, we had to use an ice table and the base dissociation constant to figure out what our final, or in other words, equilibrium concentrations of each thing will be, including OH minus ions. Finally, we could then use that concentration of OH minus ions in the pOH equation and use that to figure out our pH. If we instead had a weak acid, we'd be doing the same thing, but would be using the acid dissociation constant to find the equilibrium concentration of H plus ions and then using that to find the pH.